So, hi everyone, welcome to the Paris project. We are Ruoyu Lan, Sacha Moreau, and myself, Olivier Faber, and we're looking at low carbon climate adaptation strategies for Paris city center. As a short introduction, we will have a look at the architectural context and at global warming. So in terms of architecture, Paris center is understood as this area, which is 10 kilometers across, which is rather small. And if we were to zoom onto a typical neighborhood, this is what we would see. A rather dense fabric composed of large boulevards, smaller streets, and a variation of city blocks that share a lot of similarities. These city blocks, often called Haussmannian blocks, are inherited from Paris' grand embellishment during the 19th century that was designed, among others, by Haussmann himself. So as you can see here, every neighborhood is composed of streets, buildings, and courtyards. And the reason behind that is partly climatical. Indeed, while the street will always heat up more due to a lot of solar gains, the courtyard will always stay cooler. In section, this produces a natural flow of air between the cooler courtyard and the warmer street. However, in the context of a warming climate, where Paris has recorded the two hottest summers of its history in 2018 and 2019, we're concerned that the repeated heat waves could cancel this citywide natural ventilation system. If we look at Eurocortex ensemble data, it shows that under the scenarios RCP 4.5 and 8.5, the number of heat wave days in Paris could be multiplied by a factor of 8 by the end of the century. So in that context today, we're asking the question, how will the future climate in Paris affect the city's natural ventilation? And what passive resiliency strategies could maintain thermal comfort while mitigating the energy demand? So we will first start it by doing climate analysis to understand how such warming climate would affect future thermal comfort, and then we will test a few mitigation strategies for that temperature increase.
So we know from future climate projections that there will be more extreme heat events, and this will directly impact how uncomfortable we feel in terms of temperature. To know the potential thermal comfort in Paris City during the extreme hot days and inform sustainable strategies, we use an integrated framework which includes a urban climate model called TEB Surface. It is a physical urban weather model that simulates the heat and water exchanges between a city and the atmosphere. It simulates the effect of extreme heat on outdoor temperature. TEB Surface includes a building energy model based on Energy Plus, which simulates air temperature inside buildings and energy use for air conditioning. And it also includes a land use and transport interaction model, which is called NEDAM2D. This model simulates urban expansion and the distribution of the population in Paris city urban area over the 21st century. So we use this model framework to simulate outdoor thermal comfort in Paris for typical heat waves with strong AC use, and the impacts of adaptation actions like retrofitting the buildings, adding more vegetation, and moderate AC use. So this is an example of outdoor air temperature at 2 p.m. for a heat wave similar to the one that happened in 2003 in Paris. In this simulation, no AC is used in the city, and we can see it's already very hot, especially in the city center. If we now suppose that AC is massively used to cool buildings, it would be like a steamer outside, even during the night. The city center will still be above 28 degrees Celsius. So with strong AC use, such strong AC use not only increases high heat stress conditions, but also increases of about 22.4% annual electricity consumption for commercial and residential buildings. To prevent people from suffering from such significant degradation of external thermal comfort and relieve the city's burdens of energy use, we looked at a group of adaptation actions. So here is a change of average outdoor temperature from different scenarios. When no action is taken, the temperature will be over 42. And after we add vegetation on the rooftop and in the streets, with which a lot of people might have thought it would be very useful, the temperature only drops for like 1 degree. What really gave us amazing drops in temperature are building insulation, reflective material, and moderate AC use. With these three implemented, the outdoor temperature can be further decreased by 3 to 4 degrees. Now let's look at the individual contribution of each action in saving energy consumption. So under baseline scenario of strong AC use, we have 120 gigawatt hours more energy use per day, and adding vegetation either on the rooftop or in the streets doesn't actually save us much energy, whereas improvements in buildings and behavior changes have much more impact on saving energy consumption. The original thermal discomfort is around 16 hours per day. In terms of added thermal comfort, vegetation now has a higher contribution, but overall, more insulation and reflective material, as well as reducing AC use, are more effective. When implemented together, these actions described above enable significant cooling of outdoor air temperature, up to 7 degrees. However, it seems difficult to rely on these actions to totally replace AC energy consumption, because we can see in the city center it is still around 30 degrees, which is why we will focus on here in later building simulations. On the other hand, we also find that when combined together, these actions enable its potential energy consumption to be reduced by over 50% and adding half an hour of thermal comfort. With this, we step further into building resilience strategies.
So we can conclude from these that our efforts should be primarily directed towards building insulation, reflective roof, and a moderate use of AC. In the light of this, let's jump into the core of our mitigation strategies. We will first present you our proto-block. So these are views from the neighborhood where we implemented, south looking over the Tour Eiffel and east looking towards Montmartre. Going back at our simulation, you can see that this is the site we chose is located in the district that is the most affected by the heat island effect. So this is the proto-block that you can see in context. We will be running most of our simulation from this typical building, whose section shows 6 stories high, a courtyard side and a street side. So one word on our approach to renovation. In a country like France, in which 70% of the electric grids comes from nuclear, there's an abundant amount of electricity, and necessarily the price of electricity is kept very low, down to 0.15 euro per kilowatt. In comparison, in Germany, for example, that has recently closed its coal plant, the price of electricity is way higher. The consequences of that is that the time for return on investment through energy saving for a citizen that reduce its electric consumption is very short and attractive in Germany, while in France, the same reduction in energy will have a very long return on investment. So in the mind of a Paris building homeowner who's looking for thermal comfort, going for an active system would always be cheaper because it requires no investment, and also because the price of electricity is so cheap. But we have seen the consequences of a wide use of AC. So if we want them to go through the expensive building renovation necessary, we need to have another argument than the sole saving on energy bill. This is why we think it's important to better the overall quality of the building, as it will create 2 tangible incentives, which are increasing the value of their real estate property and increase the overall comfort beyond the thermal comfort that they will have in their home. So for that matter, we will first study at the current building in Paris. It will be our baseline. And then in our renovation proposal, we will increase the window to wall ratio in the courtyard spaces to 40% to increase daylight inside and the quality of the building. And finally, we will propose on top of that renovated building 2 additional floors that, once sold at market rate, could be able to finance all the thermal retrofits. So as you can see, we will study the baseline first, then operate most of our renovation to our renovation state, and finally just add the sur elevation. So let's look at the baseline. You can see here on the street side that the wall is often highly ornamented. It often has double glazing as it was added over the past century because of the increasing noise in the city streets. And it's composed of 60 centimeter of load-bearing stone, which gives it a massive thermal inertia and makes it actually not that bad for a non-insulated wall. It is said that some of these Osmanian walls perform better than insulated buildings of the 70s or 80s. But on the courtyard side, however, there's a huge improvement potential as the wall is still single glazed and just has 30 centimeters of brick. So
overall, in our baseline scenario, given the tough climate in this neighborhood, we can see that the low efficiency of gas boilers and the predominance of natural ventilation to achieve cooling, and the fact that French people overall consume 120 liters per person is quite negative for the typical Paris building. And in order to achieve the necessary comfort by 2035, given that there are 1,567 hours of discomfort in 2020 because of the reliance on natural ventilation, we see that we need to integrate cooling in some way, as Ruoyu pointed out. Therefore, our main changes will affect the envelope, the windows, the lighting, heating and cooling, boiler system, and the behavior towards equipments across buildings in order to verify that the window area increase and the stair elevation stay economically beneficial and thermally beneficial to the users.
So now let's look at our renovation. Given the stringent laws of historic preservation that protect ornamentation on the facade and the fact that the street wall is not performing that bad, we will not change its composition. On the courtyard side, however, which, as we have said, we increased the window to wall ratio to 40%, we're adding a 20 centimeter isolant and a double glazing on top of doing all of the above, the below. Yeah.
So because we see a major issue coming from overheating and losses, our insulation will be necessary to influence the buoyancy effect of the massive facade, which can be beneficial to an extent, coupled with the ability to contain the cooling that we want to achieve. So by improving light loads from 23.8 watts per meter squared to 2.9 watts per meter squared, improving our insulation, glazing, heating efficiency, and cooling efficiency by
That's Sacha only, or is it for everybody? Otherwise, Olivier.
limiting.
Yeah,
overall
Sacha, I think we
much
just lost you for a bit.
Oh, sorry. I'll start over. So I was saying that by improving the light loads from 23.8 watts per meter squared to 2.9 watts per meter squared, and improving our overall envelope, coupled with changes in heating efficiency and cooling efficiency, and changing the boiler to mainly an electric boiler with Energy Star rating, we're able to tremendously reduce the loads for the building and achieve very positive CO2 levels in this design.
So let's finally look at our stair elevation strategy. So we're adding two market rate floor. We're keeping the renovated building. We're just adding these highly performing floors on top. And this time, the street facade and the courtyard facade can be treated similarly for the first time. And it will be a highly efficient, low embodied carbon wall with triple glazing.
And so successfully, the stair elevation of all buildings is actually improving the overall comfort of our occupants, reaching only 176 hours of discomfort by 2080, given the changes. And in conclusion, for the overall modifications that we're able to achieve to the walls, lighting, boiler efficiency, equipment, we're able to reduce the overall AUI. And the shift in equipment usage will also have an even further impact if we start to believe that people will begin to treat their equipment with a more reasonable fashion.
There are three interesting places here to look at. The first one is the biggest drop that we have is the insulating wall from the baseline to the first renovation, which is the biggest drop. A second huge drop that we gain is the one from changing the boiler to an electric boiler. And I think what's interesting to notice is that adding a bigger window to wall ratio, increasing from 25 to 40%, is actually not augmenting the overall EUI of the building per square meter. One word on SDA as well. So we just wanted to have a modelization of the lighting that gets into the lower ground floor, as it might be impacted both by the opening of the bigger courtyard windows and also some light blockade with the SIR elevation.
So the EUI will actually remain low over time despite these changes, and it will also be beneficial for investment and profit returns on the overall architecture.
It's interesting to notice that the SDA get from 4.2 to 5.4 here, and then drops a little bit, but it still stays better to have bigger courtyard windows and a SIR elevation for the whole ground floor than staying with the current situation. And so here you can see our EUI of the 3 building. We reach under 100 kilowatt hour per square meter for the SIR elevation, but renovation and SIR elevation relative to square meter operate quite the same way.
And so therefore we can see that the SIR elevation, the window increase and envelope efficiency tied to a reliance on heat recovery and electric grid energy are beneficial to users and investors on the future. And the climate will ensure returns and climate adaptivity. So the more behavior changes are added, the better to benefit the existing users and future residential pressures that we can see in the next graph. That essentially, as Olivier was saying in the first part, even though there is a reliance on nuclear energy, if we begin to integrate heat recovery, we even begin to notice a positive impact on returns for the occupants of the building, in addition to the future residential profits that would be achieved through this elevation and improvements.
Thank you.